In this video, we are going to learn about the behavior of fluid as Newtonian fluid and non-Newtonian fluid. We will learn how a fluid can be differentiated, how a fluid can behave differently with respect to different shear rates. Now, we are going to classify the fluid with respect to Newtonian fluid and non-Newtonian fluid. How that can be done? So the fluid which obeys Newton's law of viscosity. What was Newton's law of viscosity? It was tau is equals to mu du over dy. If you remember this Newton's law of viscosity, if it is obeyed, then the fluid will be known as Newtonian fluid. But if it is not obeyed, is tau is not equal to mu du over dy, then the fluid will be termed as non-Newtonian fluid. Then it will fall into this category. Now, the fluid which does not obey Newton's law of viscosity, that can further be categorized into two major categories: time independent and time dependent. That the effect of time is negligible, then it is time independent. And if the fluid properties behave differently with the passage of time, then it will be termed in time dependent category. Now, this category can further be classified, but before that, let me tell you that if fluid is non-Newtonian, then how they can be represented. So, remember, for the cases of non-Newtonian fluids, for non-Newtonian fluids, we have this equation tau is equals to tau naught plus, here we need to write k multiply by du over dy to the power n minus 1 multiply by du over dy. So this equation is important for the cases of non-Newtonian fluid. And let me tell you that this particular term, which term? This particular term, this is known as, what we call it? We call it neta. That is sometimes also known as apparent viscosity. Remember this. And there are a few other things which we should know, that this k, what is this k value? So this k is known as, k value is known as flow consistency index. And there is one more term, that is this n. So what is this n value? So there is difference between neta and n. So this n value is known as flow behavior index. Flow behavior index. So basically this law is known as power law. So any non-Newtonian fluid can be expressed with respect to this law. So this we will see in detail, that the values of n will vary and tau naught, they will be different for different fluids, and we can categorize fluids on the basis of those. So now we will see when it comes to the Newtonian fluid, we have already seen that tau is equals to mu du over dy. So we need not to worry about this, but our area of interest is as of now this non-Newtonian fluid. So when it comes to this non-Newtonian fluid, then we have already seen that equation, that power law, that it will not follow this Newton's, but it will follow tau is equals to tau naught plus k du over dy to the power n minus 1 into du over dy. Sometimes this can be written as directly du over dy to the power n. So we need not to worry for that. We just take it as, because I wanted to write it in terms of apparent viscosity, so I have written it in this manner. So this we should know. Now we will see the effect of this n value. How this n value, how this n value will change with respect to different fluids. So when it comes to this time independent fluid, so these are pseudoplastic, dilatant, and Bingham plastic. So we should know that for pseudoplastic fluid, tau naught value will be 0. For a dilatant fluid, tau naught value will be 0. But for Bingham plastic fluid, tau naught value will not be 0. But for pseudoplastic fluid, the value of n, for the pseudoplastic fluid, the value of n will be less than 1. While for the dilatant fluid, the value of n must be greater than 1. For Bingham plastic fluid, the value of n will be equals to 1, exactly equals to 1. So this we should keep in mind. Now, when it comes to time dependent fluid, so this is thixotropic fluid. Here again, tau naught value will not be 0. Rheopactic tau naught value will not be 0. But at the same time, here the thixotropic fluid will show the behavior as n value is less than 1, while in rheopactic n value is greater than 1. So these are the basic things which are important from objective point of view. The questions can be asked from those. Now we will have a look on the different fluids. So as you can see here, we can easily identify the fluids. So the very first fluid which I'm gonna show you is this. This is Newtonian fluid. This is Newtonian fluid, right? It obeys Newton's law of viscosity. So this line will be Newtonian fluid. While this n is greater than 1, we know that this is dilatant. N is greater than 1 will be dilatant. Dilatant fluid, which is also known as shear thickening fluid. We should keep in mind. Now at the same time, we should also think of this fluid. This fluid is actually pseudoplastic fluid. Pseudoplastic, or it is also known as shear thinning fluid. So we will see them in detail. This is shear thinning fluid. We will see them in detail. But as of now, this fluid here, this is known as Bingham plastic fluid. Now pay attention that a Bingham plastic fluid is something which shows initial yielding resistance. Initial yielding resistance as this tau naught. But after that it behaves like a Newtonian fluid. So you should keep this in mind. This is sometimes also called ideal plastic fluid. Now we talk about this fluid. So this is called thixotropic. This is thixotropic fluid, and this fluid is actually known as rheopactic fluid. So remember this thixotropic and this, they both are time dependent, which we have already seen. Rest all others are time independent. Now we will move on to Newtonian fluids. So simply it obeys Newton's law. Viscosity is dependent of temperature but independent of shear strain rate. So shear strain rate is something how hard we are hitting or how much shear force is applied. So that is something which we will see with the help of one example. But viscosity is a property for Newtonian fluid, not for non-Newtonian fluid. There are examples like water, air, gases, kerosene, petrol, diesel, and ethanol, which can be treated as Newtonian fluid. Now, when it comes to non-Newtonian fluid, so the first fluid we are going to observe is dilatant fluid. Dilatant fluid is shear thickening fluid. That means it increasing its resistance with increasing strain rate. If we increase the strain rate, then it will increase its resistance. This is very good example. The cornstarch. If we talk about suspension of cornstarch, it will be a dilatant fluid, sand in water, or the classic case is quicksand, which stiffens up if one thrashes about. Now, I will show you this dilatant fluid with the help of one example. So we will take this example of dilatant fluid, which are also known as shear thickening fluid. Now we will try to understand why they are called shear thickening fluid. See, in this example, the first case, a golf ball is just gently placed onto the surface. So what we see, it sinks. Basically, it sinks pretty easily. Why? Why is that so? Because in this case, in the very first case, we know that shear strain rate is less. So that means if shear strain rate is less, that means it will offer less resistance, or we can say less viscosity. Here viscosity will also be less. But the second case, if you see, the object is actually placed from some height. So it is coming with more velocity. It will offer more impact force. That means in this case, shear strain rate, shear strain rate is increased. So we can see that if that happens, viscosity of the fluid also increases. You see, the moment this ball strikes the surface, so immediately it's not going to sink. It will wait there for some time and then after that it will gradually sinks. But in the case of third example, here shear strain rate, shear strain rate is actually very high because we have thrown the ball with a large force. So what happens? The moment it strikes here, then immediately the surface is almost behaving like it is a solid. It behaves like a solid and the golf ball actually rebounds. The golf ball actually rebounds. So this is the classic example to understand the dilatant fluid. The same thing happens with the quicksand. You remember what is quicksand? Quicksand is also the same. If someone goes on the quicksand gently, then he will start sinking. The moment you start movement of your body in panic situation, then it will behave like a solid surface. So it makes it difficult for a person who is sinking to come out of that quicksand. So that is also one of the example for quicksand. Next is non-Newtonian fluid, which is pseudoplastic. So this pseudoplastic fluid is also known as shear thinning fluid. That means it is less resistance at higher strain rate. If we increase the strain rate, its resistance will decrease. So there are many examples like polymer solutions, colloidal suspensions, paper pulp in water, latex paint, blood plasma, syrup, molasses, and ketchup. Ketchup is actually classic case because ketchup can behave like many fluids. With respect to time, it will vary its properties. Now we will learn that how a pseudoplastic fluid will behave. So this is the example of pseudoplastic fluid, that is also known as shear thinning fluid. So see this, in this case the golf ball again is gently placed. Then this surface is actually more viscous. If shear strain rate is low, so in that case the fluid behaves like more viscous fluid. So viscosity is actually more. But if shear strain rate is more, if you throw the ball into this ketchup, this is basically ketchup, you might have seen. So it ketchup shows different properties. So I have already kept it in a bowl. The ketchup is already kept in a bowl. So in that case this ketchup will be less viscous when you throw the ball with high shear strain rate. Then the fluid viscosity will be actually less. You can see it is completely opposite from the previous example of cornstarch solution. Non-Newtonian fluid, and that is Bingham plastic. So Bingham plastic already we have seen. The plastic substance is one that requires a finite yield stress before it begins to flow. Bingham plastic shows yielding followed by linear behavior, but non-linear flow can also occur. So there are possibilities. Now, like the classic case is this toothpaste. All of you might have seen this toothpaste. So when we want toothpaste to come out of the tube in which it is stored, we first need to apply some stress. After that, it flows smoothly. But before that, to initiate the flow, we need to apply some shear stress. So that is Bingham plastic. Next is thixotropic. So when we talk about thixotropic, we should know that thixotropic fluids have time-dependent viscosity. It shows an increase in apparent viscosity with time, and we have already seen what is apparent viscosity. The examples are printer ink, certain paints, and enamels. When we talk about rheopectic fluids, so they are also non-Newtonian fluid, but rheopectic fluids have time dependent viscosity. It shows an decrease in apparent viscosity with time. The example of rheopectic fluids are gypsum paste and lubricants. There are many more examples which you can think of, but this is all about the classification based on Newtonian and non-Newtonian fluids. Thank you. You guys.